Thank you all for coming. I'm going to talk about reducers today. As you know, this is a substitution because somebody couldn't make it to talk about LMAX, disruptor. So they got me in because they wanted to make sure they still had a talk that would filter out only the most hardcore people. I don't know if you'll get a T-shirt when you leave or something, but that's where you are. I just quickly before we get started, how many people here know Clojure? How many people do not know Clojure? Of the people who don't know Clojure, do you use a language like Scala or Haskell that has higher order functions? Who here does not use a language or have access to a language with higher order functions? Nobody. All right. So self-selecting crowd. That's perfect. While this library is fundamentally a Clojure library, the ideas that underlie it would cross any language that has higher order functions and collections. So the motivation for this work is simple. It's performance. There are two things we're looking to get by moving to a different framework for manipulating collections. One is just to have some efficiency improvements over lazy collection processing, which is what Clojure does by default. But the bigger motivation is to try to move to a set of collection operations that can be parallelized and eventually leverage fork join. Because as we know, computer clock speeds are stuck. And I think everybody knows the old joke about, how do you make your program faster? You wait 18 months, and the new computers make it faster. But that joke is now not funny anymore, right? Because that's not happening anymore. And so the trick is, for Clojure and all the programming languages, how do we get that back? I mean, they are making denser chips, and the chips have more cores on them. But that's not necessarily helping. Well, it's not helping a sequential program at all, right? A sequential program with the same clock speed on a new computer does not get any faster. And we've been sitting in sort of a queasy interim period here where, our businesses are buying new computers and our software's not getting faster, but eventually they're going to be like, hey, wait, I do remember 10 years ago when every time I gave you a new computer, all the software was twice as fast. That's not happening anymore, and what are you going to do about it? And it really matters. All programming languages that want to be viable in the future have to have an answer for this. So what we're trying to do here is provide a model for collection processing that's as similar as possible to what we have already, because we like that and people are familiar with it, and to leverage parallelism. There are two big inspirations for this library. One is the Haskell iterate and enumerator work. This is some great stuff. These papers are linked to from that first link. Describing the work. Some of it's pretty dense, admittedly. But it was the first thing I remember that took the work of reducing operation and it really reified it into a thing that you could talk about and say, well, this is the properties of that thing, the iterate. The other thing that was really inspiring was Guy Steele's talk from 2009. If you haven't seen it, you should definitely watch it. He's so mild-mannered, but essentially it was a condemnation of what we're doing today. Basically saying all of the sequential processing we're doing, and it doesn't matter what language you're in, whether you're in Java and using iterator, or you're in Clojure or Haskell and you're using map and fold left or fold right. These things are all inherently serial and therefore not amenable to parallelism, and we have to break free of that. But what do we do? Do we need new collections? Do we need new algorithms? Do we need new libraries? So just a little bit of history of how we got here. Again, this sort of has a functional programming bent, but it's that's the history of programming too, right? Lisp was an early influence, and it was built around one data structure called the list, and it had a mathematical basis for processing that was based heavily on inductively defined data structures and recursion. And Clojure is derived from this heritage, as is Haskell and Scala. And in Clojure's case, we have seeks and laziness. And all of these things, lists and recursion, are inherently sequential. They're about take one thing, do something to it, then connect that to the result of processing the rest of the stuff. in a row. And it doesn't actually matter if you're doing this imperatively by bashing on an accumulator or functionally by generating successive results, that those both are still sequential operations. It's not like functional programming has made this non-sequential, miraculously. But the future is more cores. As I said before, the speed has to come from parallelism. And do we need something else from the model? So we should look a little bit at the model. We started with bashing on accumulators, right? We had assembly language, you had a little register there, and you had goto, and it was like a party, right? Just keep going around and around, bashing on that thing until it had the answer that you wanted, then you were done, which is a sequential operation. And languages like Lisp and the successors and functional programming languages lifted that up to higher order functions operating on lists. Eventually, languages like Clojure and others lifted that again to say, well, you know what? We don't really need your data structure to be a list. If you could meet the algorithm at some interface or abstraction that the algorithm was happy with, we could process you. And so that abstraction for Clojure is the sequence. But for other languages, it might be the iterator or the stream or something like that. But the idea was if a collection can turn itself into something that can be sequentially accessed, then you could take an algorithm that was built around sequential access and connect the two together. So now you have higher order functions operating on collections. And those functions have names like map, right? Map takes a function and applies it to every element of a collection and gives you a result for every element as a new collection, usually as a new sequence type or list. And where we want to go in evolving this model is to have even more independence from the collection representation. I'd like to get as far away from collection representation as we can, but the real key for getting to parallelism is to get out of the order business. And that order dependency is really where we struggle right now in the way our current operations are defined. So this is that map function I talked about, right? Map being a function that takes a function and some collection, and it will, this is a classic definition in Lisp, but it basically means take the result of applying that function to the first item in the collection and attach that to the result of mapping that function onto the rest of the collections. This is the classic recursive definition of map. And while it's a very small function, basically a one-liner, it does way too much, right? And it possibly promises too much. First of all, it works recursively. It relies on order in several respects, right? So that call to first and the call to rest is utilizing an abstraction that the collection provides for accessing its elements in order. The whole notion of first is an order-sensitive thing. In Clojure's case, this function is also lazy and promises to be lazy. So that also has order dependencies, right? So if it's lazy, that means I have an expectation that if I've only consumed so much of the result, only so much of the work has been done. Again, there's order in that sentence. So much of the work from the start, from some point, the beginning. This definition is based upon a Clojure abstraction called a sequence, but logically, this classical definition is map is defined in terms of a list, right? Same thing for Haskell, right? Map is defined in terms of a list and a singly linked list. So it consumes a list, right? It's past the collection. In Clojure's case, we don't have to have an actual list. We can meet at the sequence abstraction or iterable. You can say anything like that. But it consumes a sequential thing. It's defined by saying, I will consume a sequential thing. And in addition, it builds a list, right? So map has a return value. What does it return? It's going to call this function. It's going to make an answer for the first element in the collection, and then it's going to attach that to the result of doing the rest. It's actually building a singly linked list in this case. And that's what cons does. It builds little linked list cells as it goes. So this does too much. Now there are other functions that also process collections and process sequences. A very important one is reduce. Depending on your programming language, this might be called fold left or fold L. And this function takes a function and an initial value and a collection. And the logical model is similar to map. I mean, the classic definition is also a loop over a sequence. And what reduce does is it says, take the initial value and the first item in the collection and apply the function to them. So you get an answer so far. Then take that answer so far and the next item in the collection and apply the function to that. And you get the next answer so far. And keep doing that until you've processed the entire collection. Different from map, where you get an answer for every element in the collection, reduce is going to produce one answer for the entire collection. So you can, for instance, say reduce with the function plus with the initial value 0 and some collection. That's a way to say sum using reduce, right? Because it's going to add the first thing to 0, add the next thing to that result, add the next thing to that result, and so forth. And you've now added all the numbers using a higher order function like reduce. In Clojure, we've moved away from that definition of reduce based upon a sequence definition. In other words, it's no longer meet me at the sequence abstraction. Instead, this uses a Clojure technique called protocols, which is an open form of polymorphism. If you work in a language that has type classes or something morally equivalent to that, it's the same idea. There's a protocol that says, this is the way you can tell me that you know how to reduce yourself. And the cool thing about protocols is you don't have any derivation stuff. You can say strings know how to reduce themselves by externally defining this protocol for string without touching the string class. So defining reduce this way is really powerful because now we've gotten some independence of the collection structure. Right? We're not actually meeting at an abstraction. We're not meeting at the sequence abstraction. Reduce itself, I gave you the example of sum, but reduce can build anything. You can reduce where each step adds something to a collection, and the result of reducing is actually another collection. That's done all the time. So you can really build anything with reduce. Although another critical aspect of reduce is that it's not lazy, so we're stepping away from laziness. But it's not going to get us all the way there, because we said reduce starts with that init. And it says take the init and the first thing. So those sentences, those phrases are now still full of order dependence. So we need to get away from that. Well, but at least this definition lets the collection drive. It's gotten us some collection independence. So I want to talk a little bit about the reducing function for people who may not be familiar with it, because this entire mechanism is based around manipulating these reducing functions. So we said you could reduce with plus to get a sum. So plus is a binary operator. It just takes two things and returns an answer. And a reducing function is essentially that, right? It's a binary function that takes two things and returns an answer. But there's a certain interpretation or semantics to the arguments to the reducing function. That is that the first argument is the result so far, and the second argument is the next thing to incorporate into the result. And it ends up that actually matters quite a bit when you want to try to define things in terms of manipulating reducing functions. Because plus, there's no real difference between two arguments to plus, right? You can swap them around. So it doesn't have this semantic, but reduces use of the function plus has this semantic. It considers the first argument to be the result so far and the second argument to be the new input. Right? And I described what reduce does before. Everybody clear on reduce and what a reducing function is? Because it's going to get a lot thicker fast. Okay, so what we're trying to do now is to come up with a new definition of things like map and filter and these classic functions that are completely collection ignorant and order independent. And so the idea is to build on reduce. We already saw that reduce, as currently defined, is kind of like a universal collection manipulator, and using something like a protocol or a type class means that you can pawn off any collection knowledge on somebody else. So now your algorithm is going to be independent on that. But we want to avoid the order problems of reduce. Because map and filter really don't care about order. right? Map is just supposed to produce a result for everything in the collection. Filter is just supposed to produce some new logical collection that might be missing some stuff. They don't actually care about the order. They just accidentally had the order incorporated. But there's this, so we can get that out of using reduce by just ignoring the fact that reduce, as classically defined, has an order definition, an order dependence. In other words, if you define map in terms of reduce and you ignore the fact that reduce promises to do it in a certain order, well, you haven't been poisoned by that order dependence. So we're going to start by building on reduce and eventually eliminate the order dependence. But we have to start by ignoring it. We have to make sure we don't write any code that cares about it operating on the first thing first and the second thing second. We're still left with the fundamental question, though, which is, if we're going to redefine map in terms of reduce, what should we return? Right? Because we had two ordering problems and two collection dependence problems with map. One was on the input side. We depended on taking a list or a sequence or something that could meet us there. The other was on the return side. We had to build something concrete. And it ends up that the answer to this question is to define map in such terms that it doesn't actually build anything concrete. And that takes us to the fundamental idea. The fundamental idea is that we can define map and filter instead of as functions of collections to collections that produce concrete collections, as something that instead takes a collection and changes what reduce means for that collection. In other words, you have some collection. Maybe later you're going to reduce it. If I map some function on that collection, I could implement map by just changing what reduce will mean later for that collection. And every time I get to this point in the talk, I get the same look comes over the audience. They're like, what just happened? What are you talking about? I was like, so good, now it's all bad. And so the very first time I gave this talk, right now, I made up a thing, and it seemed to have worked. It's worked 3 times since, so I'm going to do it again. I'm going to talk about the guy who makes pies. So there's this guy who makes pies. He's the pie maker guy, and he has an assistant, the pie maker assistant guy. And the assistant has a bag of apples, right? And the pie maker says to the assistant, I'm going to make a pie out of those apples, but when I do, you have to make sure that you take the stickers off the apples, because they all have stickers now. They're organic, and to make them so that you know they're organic, they put this nice inorganic sticker and glue on them, right? Organic. So take the stickers off, right? And only keep the good apples. Don't keep the bad ones. Right? So those two things, the first one, take the sticker off every apple. What is that? That's map, right? And throw out the bad apples and only keep the good ones. What's that? That's filter, right? So the pie maker has told the assistant to map and filter the bag of apples. Now, the assistant, like any good programmer / pie making assistant, is lazy, right? He's like, all right, I could right now take every apple out and take the stickers off and put them in another bag. And then I could take that bag of apples and I could go through that bag and take the rotten ones and throw them out and put it into another bag. And then I'd have a bag. And then when it was time to make pies, I could just hand those apples to the pie maker. Or I could go play Minesweeper for a little bit. And when it comes time to make the pies, when the pie maker asks me for an apple, I'll take one out and just like take the sticker off and look at it and like, okay, here you go. I'll do it then. I'll just wait. In other words, that instruction to map, remove stickers, and filter for good apples is a recipe, right, that can be applied only when we reduce the bag of apples into pie. We don't actually have to make different bags of apples. We don't have to move the apples around. All right? That's the idea behind this library, is that we can implement map and filter by just changing what it means to make pie. All right, so what does that look like? The library actually doesn't do this code exactly, but I've written this code explicitly because macros make this stuff go away, and you can't see it when you look at the library code. But the real key here for me in designing the library was to try to find what is the fundamental definition of what is mapping. What does mapping mean? What does it mean to map something? And so if you tried to say, if I was going to have a function called mapping that implemented this idea, what would it look like? So it would be a function, we want to map some function. Right? That function might be something like take the stickers off the apples. Right? We want to define this function by returning a new function, right? That says, when you give me a reducing function, like make pie, right? I'm going to give you back a reducing function, right? Which is a function of a result and a new input that will call the function you gave me, make pie. But before I do, this is the pie so far, I'm going to take the sticker off. That's the essence of mapping, right? It's given some function, take the sticker off, and we're going to say now that all it does is it changes the meaning of a reducing function. Given some reducing function, I'm going to return a different one that's going to actually use the reducing function I was given after I've mapped that function on the input. This is the essence of mapping. What's really cool about this? Where's the collection? What collection? It's gone, right? So that's good, but mapping is probably the easiest case. There are two other categoric cases that matter, right? One is where you have some stuff and you end up with possibly less stuff. That's what filter does. So can we do the same thing for filter? What is the essence of filtering? Right? Filtering takes a predicate, right? Is the apple good or is it rotten? Right? And same thing, we're going to say, this is going to return a new function that when passed a reducing function like make pie, will return a modified reducing function. So this is just transforms. It takes the make pie and it says make pie out of non-rotten apples. Right? It's just transforming your reducing function. It's going to take it and return another one. And it's going to do the predicate. It says, if the apple is good, include it in the pie. Otherwise, what? Don't. What's really critical here, though, and we just had to talk about map reduce. Does this return like an empty bag of apples or something like that? A little Ziploc, right? Does it put every apple in a Ziploc and then sometimes gives you an empty Ziploc? No, it does not. This is very important. There's no junk in the middle of this. Filtering means don't use it, not make emptiness. Okay? So that's the filtering case. And what about mapcatting or flat mapping? It depends on what language you use, what you call this. So what is mapcat or flat map? Right? Is like map. It takes a function and applies it to every element in the collection. But the presumption is that that function returns for each element a collection itself. And what you want is all the contents of those collections without the collections around them anymore. That's what flat map or mapcat does. So how do we do that? That's the other tricky case, right? That's the expansive case. So we've looked at the one-to-one case, right? We've looked at the possibly reducing case, or I should say eliminating or filtering case. And now that we have the expansive case. So it's the same thing. We're going to say, somebody gave me a good example of what this was. Oh, chopping the apples up into pieces. That's it. So that's what we want. Now we're going to say we want a mapcat slice up the apple. Right? It's going to produce more than one slice per apple, which is going to take some reducing function like make pie. It's going to return a new reducing function that, given the pie so far, is going to slice up the apple and then do what? Put every slice into the pie. And so we can just use reduce to do that job. In other words, what does it mean to have an expansive transformation function? It means operate on the result more than once. So filtering might not operate on the result, and expansion might operate on the result more than once. But note, this doesn't actually return what from each guy? A little baggie of slices of apples, right? No, it just puts the slices right in. So it's very important. This is This is much different than what you see from some other libraries that are sort of mapping oriented that must produce collections for every step. So I think one of the things that's really critical about this is to look at what's in common between these things, right? So what's all this stuff? It's all what? What do we call that? A legal term. Boilerplate, right? We're working in a language with macros. What's going to happen? They're going to become victims of macros. That's just going to go away. When that goes away, when macros make that something that you don't have to write, what exactly do you have to write? What do you have to write to define what map is? Just that little purple part. Right? Is there possibly a smaller definition of what mapping is than that? I don't think so. How about filtering? Just the purple part. You just write the purple part. Right? When you get your fancy new parallelism libraries from your language designers, ask them, what do I need to write my own things, my own extensions, my own parallel operations? Can I just write the purple part, please? Because that's all I want to write. Same thing here. This is the essence of flat mapping. By defining it this way, as these reducing transformers. So that's basically good. I mean, we like the fact that we can handle these three cases. That's starting to smell like an answer. But the use right now is still awkward, right? Because we said that mapping is a function of the reducing function. So for instance, if we wanted to sum this collection, but first increment everything in it, normally we would say, map increment over the collection and then reduce with plus, right, to sum. That's what I said summing is. And that's what this does, but it's kind of backwards, right? Because what we have to do is say mapping inc transforming plus first and then apply that, then reduce with that. And that's not actually what we want to do. That's awkward, right? We're used to, in Clojure and most other languages, mapping increment across the collection and then reducing the result of that. So we need to turn mapping into a function not of the reducing function but of the collection. But it's still going to work this way. We just need to move it over. So what we want and what we're used to is for map to be a function that takes a collection and returns a collection. But we said we don't actually want map. The guy is lazy. He's playing Minecraft or Minesweeper. I said Minesweeper. Who still plays Minesweeper? Minecraft. He's a modern pie making assistant. He plays Minecraft. And he does not want to make an actual bag of unstickered, non-rotten apples. He's busy. So we need to revisit our notion of what constitutes a collection. What's true of every collection? That's a hard question, right? What is actually true of every collection? Do they all have stuff in them? Not necessarily. Can they all give you a count? Are they all iterable or somethingable, or do they all have, nth? Almost nothing is common with all collections. It's very, very tiny. Of course, Java says this huge pile of stuff is common for all collections, but that's just Java being Java. But logically, there are very few things. A collection might have stuff in it. And in particular, it might have more than one thing in it. That's really all that's true of every collection. It might have more than one thing in it. And so what we want to do now is we want to define map like we used to, taking a collection, returning a collection, but we're going to have to get clever about our definition of collection. And what I'm going to say is if you have stuff in you, and I have something like protocols or type classes which say, if you have stuff in you and I ask you to apply this function, to reduce yourself with this function, you can. You're a collection. That's good enough for me, right? Because I can build a pile of functionality on top of reducibility. So we're going to change the definition of collection. We're not going to say a collection is iterable. We're not going to say a collection is countable or add any other fancy stuff. We're just going to say the minimal definition of collection is that you're reducible, right? Which means that you support the reduce protocol. I can call reduce on you. That's it. So now we could say, could we make a definition, given one of these transformers, could we make something that is reducible? In other words, we need to make a collection now. I don't want to actually make a bag of apples. I want to make a recipe for something that would reduce into a nice pie. I don't want to make a concrete bag. So the answer is yes, right? Because this protocol is open, Clojure has this thing called reify that lets you create an instance of a protocol. You can consider it to be like the moral equivalent of making an anonymous inner class, right? That implements an interface, right? You can make an instance of this protocol just from scratch with some code. And that's what we're going to do. We're going to say a reducer takes some collection, right? And some transformation function. So collection here is bag of apples. Transformation function is something like mapping, right? The ones we defined before. And we say, that can return a collection. If you're going to tell me a collection is only reducible, then I can return a collection given those two things by saying the definition of reducing this collection, given some reducing function like make pie and an empty pie tin, is to ask the collection itself, the bag of apples, to reduce itself with the transformed make pie. This is now make pie after taking the stickers off the apples. And here's the empty pie tin. In other words, this is a recipe for a new collection that itself is reducible. In other words, I can ask this thing to reduce itself with make pie. And it's like, as if I had a bag of apples that had all the stickers taken off. I don't really. I'm just going to, on the fly, modify the reducing function to first take the stickers off with this mapping we defined before. This thing now returns something that behaves like a collection insofar as it's reducible. It means that we can write this now, reduce with plus starting with 0, so this is sum. First making a reducer around the collection using mapping with increments. This means increment everything in the collection and then make a new collection that's a logical collection out of that and reduce. It's not quite what we want. We're going to fix that in a second. But the key thing is this. This reducer makes a logical collection that itself is reducible because it implements this protocol by just transforming the reducing function the way we showed. We know we can do mapping and filtering. What about this is going to change when we move from mapping to filtering? Does this even know it's doing mapping? Does it know this is mapping? Or filtering, or mapcatting, or any other collection? No, it doesn't. We can define reducer once. So we have some boilerplate on the prior slide. We have the definition of reducer once and once only. This is a universal collection maker. It can make a collection out of any collection and any reducing transformer. And now we've moved the transforming to be some function of the collection as opposed to a function of plus. So we're close. We're very close, in fact. It's just one more step to have something that feels like map used to feel. So I just call these R maps so they wouldn't clash with Clojure's map. But map in the new model, in the reducing model, takes a function and a collection just like the old map used to, and it returns a new collection by making a reducer on that collection using the transformer on the reducing function. A transformer that's based around the mapping function, right? That's what map is. Filter, same thing. Mapcat, same thing. Look at these things. How similar are they? Totally. What's going to happen to all that? The victim of a macro again. It's going to go away. So we have all the boilerplate on both sides of this disappears. There's one function called reducer that makes a collection given another collection and a transforming function. We have a universal recipe for making reducible collections from other reducible collections based around a set of transforming functions that don't know anything about collections at all. Not at all. And now our invocation looks the way we're used to. At least if you're a Clojure programmer, this is what you're used to, right? You say map inc across this and then reduce that result with plus. You know, you just, it's function application, and you just do this, and you can compose these things. Same thing, filter looks the same thing, a filter call. Filter out the numbers, and then sum those. Or, you know, get me ranges of all these different lengths and sum the ranges, flattened. So now we're pretty good. We now have a recipe for all these functions that's completely different than it used to be, but the invocation looks exactly the same as it used to be. And we've gotten rid of all this stuff except reduce, we know, inside is still sequential. So this is actually faster than the closure's lazy code, because this is not lazy anymore. It does not do any allocation per step. Right? You saw the way those transformers work. They weren't building boxes. They weren't building lists around things. There's no allocation per step. There's no stuff in the middle. There's nothing. So it is faster there, but I keep forgetting to change the slide. So it's supposed to say, where's the pi now? So where's the pi? Right? Well, I started this talk by saying the whole point of this is to get to parallelism. But reduce itself is not parallel. So we now have map, which is cool, but not parallel. But what's really neat about it is it's not actually doing the job, right? Map no longer does the work right then. When does mapping happen? Only later when you reduce it, right? When does the stickers get taken off? Not right now. Playing Minecraft, right? Later, right? So no concrete work is being done. So even though reduce is sequential, and when we call reduce later, it's sequential, we didn't actually put anything in mapping or filtering that cared. So maybe we can use them again in a different context. And that's how we get to the real prize, which is something called fold. And of course, fold is an old word. But typically in programming languages, it means something concrete, either fold left or fold right, or they'll call them fold L or fold R. And reduce is fold L. Closures reduce is fold L. Lisps reduce is fold L. Fold is an abstraction of folds generically that specifically says, I might work in parallel. Right? So it implements its semantics via threat. I hereby threaten you that I might operate in parallel. Right? When I do that, when I say that, what does it mean of your reducing function? Might operate in parallel. Better be associative. Right? It's going to need to be associative. So what fold is like a potentially parallel reduction. You might not always get parallelism. There might be reasons not to parallelize. You're too small. Parallelization overhead would dominate. I'm not going to bother to go that way. Or you're trying to fold a collection for which it's not amenable to parallelism, like a linked list. A singly linked list is not amenable to parallelism. That's okay, just we won't do it in parallel. So what fold is it's like reduce. Right? You're going to take a function and apply it to a collection. It's going to reduce the collection pairwise, but it's not going to start at the very beginning. It could potentially happen in parallel. And the way fold works is it uses a reduce combine strategy. It very specifically does not use a map reduce strategy, and I'll show you why in a second. Under the hood, the implementation of fold leverages the Java fork join framework. So it's going to partition the work and use the work stealing capabilities of fork join. How many people know about fork join? Okay, I'll show you a little bit of fork join in a second. So fold is very similar to reduce, right? It's a function that takes a reducing function in a collection, but fold also can optionally take a combining function. It actually has another optional argument that happens earlier, but we're going to talk about this 3-argument flavor for now, which is takes a combining function, a reducing function, and a collection. Right? And fold, just like reduce, is also implemented in terms of a protocol. So it's an open system. Basically, you say, I know how to fold myself. If you give me these 2 functions, I can fold myself. So fold just says, ask the collection to fold itself using those 2 functions. This is a partitioning size, which is optional and has a default. That's why you're not seeing n anywhere here. So just like reduce, it asks the collection to do the work, and it uses a protocol to do that. The logical operation of fold is to segment the collection into pieces, right? Then to run multiple reduces in parallel on those pieces using the reducing function. Then using the combining function to pairwise combine the results till you get a single result. And that's how fold works. And that looks like this. So you can imagine the collection is a big continuity here. Chances are, in reality, it will be a tree of some sort. It doesn't really matter. But in a functional programming language, it will usually be a tree. But of course, this works on arrays and things like that. Logically, it gets segmented. You don't actually produce these segments, but you're just going to divide it up. So, sub-vector or sub-range is, it's the same idea. The big thing is still there, but I've got a window to a little piece of it that I'm going to operate on. Then we're going to do independent reduces. Now we know reduce takes an initial value, right? And it operates on that value in the first item, then the result of that in the next item. Because we're going to be firing off a bunch of reduces in parallel, we need a bunch of initializers. We have to remember that, because that seems tricky. Where do they come from? Then we're going to use the reducing function on those. So that's a straight reduce. It's exactly the straight reduce. An important characteristic of this design is the fact that while in a theoretical model for fork join, what happens is you take the work you have to do, you divide it in half. You divide the halves in half, and you keep dividing in half till you're down to 1, and then you do the work on one and then combine it with the other. In practice, you never use fork join that way because the overhead of processing individual items at the bottom would dominate. So you always stop short of that. So the practical use of fork join always segments and stops at some segment size which is greater than 1, usually much greater than 1. But a lot of the designs around fork join pretend as if it's going to go down to 1. Right? I don't see the point of that. Right? If you're going to go down to n, and the best way to process n things is with reduce, right? Why pretend you're going to go down to 1 and process the bottom things with map? Because you're not. And when you do that, you end up with all that goofiness, right? With empty baggies and baggies with slices in them and like all those extra collections and stuff like that. We know we're going to reduce at the bottom. We know we're going to have a collection at the bottom. And the best way to process a collection is to reduce it. So this library is defined in terms of reduce at the bottom, not map. Then we'll get answers for that. This reducing function can be arbitrary, right? So if it was plus, these might all be numbers, right? If it was concatenate to an empty collection, these might all be collections. Doesn't matter. This is very general, right? Reducing and then combining. And then the combining function is another binary function, right? That takes 2 of whatever those are and returns something, and then so forth, and finally you get a result. So this is really good. Right? First of all, it breaks free from the ordered single pass, right? There's no initial value. The big difference between fold and reduce is there's no initial value for the whole job. Right? Reduce took that initial value, right? But fold doesn't. Fold doesn't take init up here. That's what's missing. Doesn't have an initial value. So we've broken away from the ordered single pass, right? That was the last piece. If we had an initial single value, we'd still have to go in order. Now we don't. We have the thread of parallelism. We can do it in separate pieces. But we do have this question, right? Where do the seeds come from? Right? These reduces have to start with something. What do they start with? Who cares about what they start with? Who's going to ultimately need to consume that? The reducing function has to be able to process it, but maybe there's nothing to reduce, right? In which case it would flow through. Who really cares? A lot. These guys. They care a lot. Right? This value here must constitute a sort of magic kind of value for these combining functions. Because imagine you had a segment here, after we filtered out all the rotten apples, there were no rotten apples, right? This value here has to flow through this function and do what in it? Represent nothing, right? It has to disappear to that function. So there's so what happens in the library is we need to have an initial value for each of those things. We're going to obtain that initial value by calling the combining function with no argument. So when you call the combining function with no argument, it returns something. That thing has a name. It's called an identity. Right? So if you think about it, the identity for plus is 0, right? You can add 0 to anything, and the result is that thing. So it's like a no-op value for the operator, right? And what you need for a combining function is a binary function of 2 things for which there's some identity, right? So the identity for addition is 0. The identity for multiplication is what? 1. Identities for like collection things are usually like empty collections and stuff like that. But it's very important, actually, that this not be a value, right? You'll hear this talked about as being a value, and the mathematical definition of this thing is called a monoid, which every time I say it, people are like, okay, did you just go tell me to, All monoid means is exactly what I'm saying. It's a binary function that has an identity value that disappears when it's used to combine. That's what it means. They have fancy words for all these things. So it's great if you want to be fancy. But that's all it means. So that's the property we expect. The property we expect of this function, that the reducing function, combining functions must be associative binary operators, and that the combining function in particular also have an identity value that you can obtain by calling it with no arguments. But by calling it, instead of saying, I'm going to give you the identity value, you can actually have identity values that, for instance, are mutable. Right? If you want to do a very high performance folding job, you might want to have array lists in there. Well, if you gave every step here the same array list, what's that going to do? It's going to make a mess, right? They can't all have the same array list. They have to call the same constructor. They don't want to have the same value. So we get the values that way. So now we have an idea. We talked about a reducer, right? A reducer is just something that takes a collection and this transforming function and makes it into something that itself is reducible. We have the same notion here. A folder is something that takes a collection and some transforming function and makes something that itself is foldable. That's all. It ends up being the case that as long as the transforming function doesn't care about order, right? Map doesn't care about order. Filter doesn't care about order. Take actually cares about order. Right? As long as the transformer itself doesn't care about order, then any reducer is actually also a folder. Anything that's reducible is also foldable. A mapping of something is foldable, right? Because map doesn't care about order. So we can define something that looks a lot like reducer, right? Called folder. It takes a collection and a transforming function. Remember, those are like that mapping stuff. It's going to reify both reducible and foldable. We can just think of them that way. Both of these protocols, and it's going to implement fold the same way. It's going to say, if you ask me to fold with this combining function and that reducing function, I'm just going to ask the collection to fold itself with the same combining function and with the modified reducing function, right? So if it ends up that the pie maker and the pie maker assistant are like master jugglers, right? And the pie maker can actually catch more than one apple at a time, and the pie making assistant can actually deliver more than one apple at a time. They can have multiple apples flying through the air at the same time and make pie at twice the speed of anybody else because they have all this juggling capability. Because it has nothing to do with take the stickers off. He takes the stickers off and he throws them at the same time. He has to be pretty agile to take the stickers off one-handed. But he's got a lot of spare time. All right? So this looks exactly like reducer before. It's just a generic thing that says I can make a folder out of a transforming function in a collection by reifying this protocol. And instead, you'll find that map and filter in the library are not defined in terms of calls to reducer, as I showed you before, but in terms of folder, which makes them both folders and reducers. Right? They can be used for both of these jobs. Right? So the cool thing here is we didn't touch mapping at all, right? Or map. We're all done with that. By making that completely collection independent and simultaneously operation independent. Are you reducing? Are you folding? Map does not care. Mapping does not care, and neither does map, because all map does is make a recipe for something you can do something with later. And it's going to ask the thing to do the hard work. All it needs to do is transform the function in the first place. You've made these completely orthogonal. That's huge, right? Collection representation, order independence, operation independence, and transformation all are independent, completely independent. We do not have parallel map, right? We don't have parallel collection. Don't have those. Don't need them. What you need is just to take stuff apart far enough so you can put it back together however you want. And that's how this works. It has some very neat properties, right? It's composable. So we can say, instead of saying filter the even numbers on the collection and then map inc on that collection and then reduce it, you can just say, make this recipe for me. This recipe is, filter out the rotten apples and take the stickers off. And we can compose those two things. You notice that these two calls are missing the collection, right? They're curried. They don't have the collection. So what you end up with is a recipe for taking the stickers off and filtering out the rotten apples, or filtering out only the good ones, right? That doesn't yet have the job or the bag of apples. It just has the recipe. So you could write this recipe down. You could give it to your friends. They could make pie, or they could make apple pie. They could make pear pie, if there's such a thing. Or they could make, I don't know, what else has apples in it? Crumble. Right? So the recipes are first class. This is first class, right? You can compose these recipes and later apply them to the collection sources. That's what you want. That's why we use functional programming languages, right? So I'm just going to beat up a little bit here on reduce combine versus map reduce. In particular, one of the things that struck me about Guy's talk was he has examples of filter, parallel filter. And parallel filter is returning all these empty collections, and it's collectionizing things. And you're going to see that, and you're going to encounter that everywhere. I think it's not a small thing that this library does not do that. I think that's what makes it categorically different from a lot of what you might see. It makes it very fast. It means you don't need sufficiently smart compilers or things to like make stuff go away, or stream fusion, or other really amazing magic. It's really quite simple. But the thing is, that's it. That could just be an implementation detail. The biggest thing is you only write the purple part, right? What else lets you only write the purple part from before? Because that's really the key win. When you want to write one of these things, you write the essence of the job. You're completely isolated from everything else. Right? So we don't have any collectionification. I talked earlier about the fact that you don't want an identity value. You want an identity value creating function. That will let you create identity values that are mutable, which is going to be important if you want to have very high performance insides, right? Because we don't care, right? Inside this job, if we bang on array lists and end up with an immutable thing at the end, that's a win, right? We don't need to be all religious inside there about functional programming. We need to produce a result in a functional manner, which means we took inputs, we didn't affect the outside world, we gave you an output, and we're going to give you the same answer every time. You can use arrays inside the middle of that. That's okay. But if you want to use arrays inside the middle of that, you can't pass the same array to every step of the reducing job. You're going to need to manufacture arrays for each step of the reducing job. And the other thing is just the granularity differences there. What happens when you use map reduce style is you end up with jobs in the intermediate steps of the computation. If I say fold a collection that I've mapped and reduced, that I've mapped and filtered, did they produce extra work for the parallelism job? No. They're gone. They're gone before the parallelism job even starts. All they did was transform the reducing function at the leaf, right? If you have a map-based system where the bottom job is creating empty collections, that's going to create work for what function? The combining function, right? The combining function is going to have to undo all that stuff, concatenate empty collections, uncollectionify stuff, flatten, and then every time you concatenate those things together, that's more work. And then the compiler guys are going to be like, oh my God, we got to make this disappear. You don't have to do that if you choose reduce at the bottom. Okay, so in summary, the idea is to revisit the ideas of map and filter as reducers, which are logical collections that are themselves reducible, that are defined in terms of making a transformer of a reducing function to another reducing function. They're now completely independent of the collections, right? That mapping doesn't know about collections. It has nothing about collections. It's just the essence of the work at a step with no notion of where that step occurs. So they have no collection dependence and no order dependence. They do not know what part, they don't know that they're part of any particular kind of algorithm. If it's happening sequentially or in parallel, they don't know, right? If your fold itself is parallel, all these operations are inherently parallel because that's orthogonal now. Parallelism is not a characteristic of map. Parallelism is also not a characteristic of the collection, right? If the collection didn't think of this and you can define the protocol fold for it, you've now added parallelism to that collection. So this works on the existing closure collections just as they stand, right? And it works with existing operations. So you don't have parallel collections, you don't have parallel operations. I'm not really sure I really believe in a lot of those things. You'll build parallel algorithms around this, but these fundamental things are independent of order, and that's where the power comes from. So you want fold, collections, and reducers all independent, and then you can compose them simply. And that's the idea. I do just want to show you how this works. So we're going to just load up this library, and we'll make a big collection of numbers. And so this first call is, this first of the three calls here, I'm here, is ordinary closure code that calls the lazy sequence function. So it's going to filter out the even numbers from the collection, then it's going to map, increment over those, and finally produce a sum. So we'll call that. Of course, this guy is the first guy to run, so he's going to get penalized with some compiling time, and we'll run him a bunch of times so we get good speed. There we go. So that's roughly where he's at. This next guy, second one, right? We're doing the same job over the same collection. Did not touch the collection. Nothing behind my back, right? But we're now going to switch to the reducer versions of filter and map. We're using the same reduce function, right? This is Legos. Take your pieces, put them together however you want. So we're filtering with the reducer and mapping with the reducer, which means those jobs are not actually happening. They're just building a recipe. And then we're going to reduce with ordinary reduce. So I'll let that warm up, and there you go. So that's faster. That's just eliminating the allocation per step overhead of laziness. And finally, we're going to now just have switched in this last one from reduce to fold. Again, fold is logically the same job. In fact, when fold can't parallelize the operation, it just falls back to reduce because it's the same logical operation. Oh, I should have said, if you don't supply a combining function, the reducing function is the combining function, because you notice this call to fold doesn't have a separate combining function. It just has plus. It means the plus is being used for the combining function and the reducing function, which makes sense, right? We can add all at the leaves and then add the results of the leaves. So we just use, and that's very convenient, right? So fold can be used exactly as a replacement for reduce if you don't have a hybrid job where you're trying to do something fancy. So we just swap for fold here, and boom. There we go. That's pretty easy. So that's it. Thanks.